Thank you again for having me here. So what I decided what I'll give you as I also understand that this FDP and it's like FDP is the faculty and mainly I'm working in the experiment and I do some theory also, but mainly I'm experimentalist. And then what I thought is I'll give you an overview of what is going on in the quantum side or mainly quantum optical side in the experiments mainly in my lab in IIST. So in particular, what I'll talk about some light that we generate that we call bright squeeze light and what are their or how we look at their quantum correlations and then what are their technological applications. So I will start from a brief introduction of what is our motivation, why you should care about bright squeeze light, and then what we do with them, and then what kind of technological advancement they can promise. So before going to actual content of my talk, just let me introduce what we are doing, just very briefly. So we have a dedicated quantum optical technology lab at IIST where we are mainly working on entangled twin light beams. It's a quantum optical technology lab. That means we have to work with the photons. So we generate entangled light beams and they are not like just a paired wise entangled, they are the beam wise entangled. We are generating really bright. In turn, they can give you beams. They are bright entangled beams and of course they are squeezed as well. And then we not only generate this kind of system here as setup is shown here, we propose them to use for quantum cryptography and quantum communication application along with quantum sensing and metrology. This is the research part we are doing in the quantum side in IIST. Other than that, of course, definitely we have a dedicated master program in quantum technology. We started since 2022, where we are training students in different aspects of quantum technologies. And of course, we are having regular academic programs, for example, BTech as well as Ph.D. and postdoc programs. So with this, I would like to give you a motivation. Why should you care about squeeze light or rather bright squeeze light? So if you look at the squeeze light or if you look at the quantum technology area and if you look at the vertical of quantum technology, and there are mainly, you would say, three verticals in the sensing and metrology. And then sensing and metrology, you can imagine that when you talk about the sensing, then the most advanced sensor that comes in our mind in the recent technology is the LIGO actually, which is detecting gravitational wave. So now people are trying to, or people have already interfaced squeeze light with the LIGO to enhance the sensitivity of those kind of sensors. Excuse me, there's some echo from somewhere. Can you please? Yeah, sure. Thank you. So, for example, the ultimate sensitivity of the LIGO, this kind of the biggest experiment of this century, I would say, is limited by the short noise limit. So, can you go the sensitivity that you have gotten from the classical light by using quantum resources? Definitely squeeze light is a solution. Then by using squeeze light, you can have sensitivity better than the classical sensor. On the other hand, what previous speaker was talking about, of course, the squeeze light are one of the very potential candidate for the quantum computation. You can use squeezer or so many squeezer to realize a quantum computer or quantum computational tool. So on the other hand, they also carry a lot of significance toward quantum cryptography and communication. So of course, you can use this squeeze light or entangled light to encrypt information and securely decrypt those kind of information. So in a sense, the kind of resources that I'm talking to you today will have application in all the vertical of quantum technologies. So with this, I would like to give you an outline what I'm going to talk to you today. So I'll give you a brief introduction. What is squeeze light? What is squeeze light and how do we generate this kind of squeeze light? In particular, we are generating this squeeze light with a 4-way mixing process in atomic vapor. I'll talk to you how do we generate. And then after that, I will show you what squeeze light can do in the fundamental science. So you can demonstrate the EPR kind of paradox with the squeeze light, which are one of the landmark experiment of last century. And at the same time, you can you can use squeeze light for the information encoding as well as quantum cryptography application. So in this part, you will cover some of the application that goes toward the quantum cryptography and quantum communication. And then in the latter part, I will highlight some of the research that that motivates you that the squeeze light can be useful for sensing application. So in particular, I'll talk about really small trace gas detection sensor or quantum gyroscopes. So these are some overview I'll be giving, but I promise that at the end of this lecture, you will get some of the ideas how things work in the real life. So to start with, so first I'll give you a brief introduction, as I know that this is really FDP, the faculty members or the students from different backgrounds. So just I would like to tell you what is the squeeze light. Squeeze light is nothing but just if you look at the quadrature component of electric field, or the electric field typically can be written in the quantum mechanical description by this kind of operator. It is nothing but it can contain cosine and sine component. Then what comes with the sine and cosine, which are orthogonal component, we call them quadratures. And these are represented by some operator in the quantum mechanics, and these are called quadrature operator. Interestingly, these quadrature operators are like position and momentum operator. They do not commute. They don't commute. That means they can satisfy the Heisenberg uncertainty relation. So you can always write, or you can always find uncertainty relation for this quadrature component like you do with the position and momentum degree of freedom. So of course, it's a normalized to 1. Now the question is, if you look at in this uncertainty relation, you are getting the uncertainty in the measurement of this quadrature and this quadrature. The product of these uncertainties have to be greater or equal than certain constant number. And then you see that there's an equality sign also. And then if you have certain state, in which the uncertainty in the measurement of either of those quadrature is equal and the minimum allowed by the uncertainty relation, these kind of state in technical terms we call coherent state, or in quantum optics we call coherent state. And then the noise label, the uncertainty label that you get from this kind of state, that label or that limit we call short noise limit or standard quantum limit. And then if you look at the same thing in the phase space diagram, they are represented by a disk actually, because either side you go, you will have uncertainty equal in those kind of state. Now the question is, can we have any state of light? Or I would tell you that the typical example of this kind of coherent state are usual laser beams. If you have a laser beam, ideal laser beam which doesn't have any noise, technical noise, ideally they will be in the coherent state. So after certain approximation, you can assume the usual laser beam at a coherent state. They typically follow this kind of statistics. Now the question is, can we have a state in which the uncertainty in measurement of any quadrature be less than the standard quantum limit? Yes, indeed, we can have this kind of state. And if you generate these kind of states are known as squeeze state. So of course, you have to always obey uncertainty relation. That means if you are reducing the uncertainty in the measurement of any of the quadratures, then the uncertainty in the corresponding conjugate quadrature has to be increased, so that the product satisfies this inequality. So this kind of state, if you look at in this one, we have reduced the uncertainty in this direction at the expense of increased uncertainty in this direction. And then of course, it's your trick that you can reduce in either of the direction the uncertainty. Either you want to reduce this and any arbitrary direction. So the point that you have to check is uncertainty in either of or any of the direction if it is less than SQL. If it does, then definitely these kind of states are called squeeze state. So this is the definition or textbook definition of squeeze state. Now the question is, how do we generate this kind of squeeze state? Again, the textbook example. So to generate a squeeze state, you can have some kind of squeezer or some kind of black box which does this kind of quantum mechanical operation. So if you look at in this quantum mechanical operation, So what you do, you start with a coherent state, you send this to some of the black box, which is a squeezer, which is squeezing. And then if you look at the quantum mechanical description of this squeezer, what it does involve, it involves A square and A dagger square. In quantum mechanics, we call them annihilation and creation operator, and they are responsible for generating or distracting photon. So if A is coming 2 times, that means it is destructing 2 photons. Or if A dagger is coming two times, it is creating 2 photons. So that means a black box that can create simultaneously or destroy simultaneously a pair of photons, then what you get at the end is a squeeze state. So this is the textbook definition of squeeze state. So now the question is, as I said, I'm creating or destroying 2 photons. Then where these 2 photons are going, if these 2 photons are going in the same mode, same direction, same spatial mode, this kind of squeeze state I call single mode squeeze state. But it is not always needed that you create a pair of photon. They may not go to the same mode. One may go in this direction, other may go in this direction. If you generate this kind of squeeze state, these kind of squeeze states are called 2-mode squeeze state. So in the 2-mode squeeze state, what happens? Initially, you start with a vacuum state. Initially, you start with a coherent state, let's say coherent state. Then you have SQL, you have a noise that is the minimum allowed by the uncertainty relation. Now, if you pass through this squeezer and if you look at the individual modes of the 2 modes, they become noisy. Why they become noisy? Because I'm saying that this black box process is creating a pair of photons. But when this pair of photons is created, that is completely probabilistic process. So you are randomly creating more and more photons, and then if you look at their statistics, it is like more random. It's a thermal. It has more noisy. But interestingly, if you look at the joint quadrature, the 2 quadrature components of 2 fields, if you look at the joint quadrature, you can see the noise reduction in their joint quadrature measurement. It could be in amplitude difference or phase sum, actually. In this way, to see the squeezing property in the 2-mode squeeze state, you have to make a joint measurement of those quadratures. And that's how we look at the squeezing characteristics in 2-mode field. Now, of course, so far I have been talking about the squeeze light in terms of the in terms of the field. Now, if you are more comfortable, or if you want to look at the same in terms of the photon picture, then what I said that in the squeezer operation is creating a pair of photon. But if you put 2 detectors here in one beam and other beam, and then if you want to detect these two photons coming out from the squeezer, then you say that you are getting a pair of photon. You are creating, once a photon is created, definitely its partner has to be created here. When it is created, that is not clear, or that is not under your control. But once it is created, its partner has to be created. Now, if you look at if you just continuously create the pair of the pair of photon in those 2 beams and detect them by 2 detectors, then you will see that the photocurrent out of this detector will be continuously fluctuating, because the temporal arrival of photon is random. So you will have a random you will have a noise in your photocurrent. But interestingly, whatever noise this beam is having, the second beam also will have the same noise, because they have the copy of that. These are the temporal correlation you can look at in a squeeze light. And then if you have a temporal correlation, you can cancel out. If you do simply difference measurement, you can cancel this correlated noise. On the other hand, you can always, instead of just looking at pin detectors, you can detect these 2 beams in a whole spatial region. So you can put a CCD camera here and switch CCD camera here. And then you can always monitor, once I'm getting a photon here, where its partner is hitting. You can look at their spatial position on the transverse plane. And in that way, you can get the idea of how spatially these 2 photons of the squeeze state are distributed. That will give you spatial correlations. So in my talk, in the coming slide, I will give you an overview of what you can do or how you can look at the spatial correlation as well as temporal correlation properties. So having said that, so there are multiple methods or many methods to generate squeeze light. Mainly this OPO, optical parametric oscillator, is one of the most common method. But what we are using to generate this kind of squeeze light or twin beam is by using a four-way mixing process in hot atom. So briefly describing what I'm doing, I interact a strong laser beam in atomic media. So I shine an atomic media by a strong laser beam, and what that atomic media does, these atoms, we in quantum optics we say a configuration that is called double lambda configuration, in which we are using rubidium D1 line of rubidium 85. So basically we have hot atoms here, and then in that hot atom, when I shine a laser beam, what happens? These atoms, which are in the ground state earlier, they absorb 2 photons from my strong laser beam. They absorb 2 photons, and then because of this four-way mixing and energy conservation, they emit 2 photons out. 2 photons are absorbed, 2 photons are emitted, and these emitted photons are entangled or squeezed photon or correlated photons that I'm talking about. And then, of course, their dynamics, where these photons will go, this dynamics is governed by energy conservation as well as phase matching condition, where 2 photons, if the initial pump photon, 2 photons are going in this direction, then the generated photons, where they will go, their direction will be decided by the momentum conservation rule. So sum of the generated photon, momentum of generated photon has to be equal to the sum of the momentum of your pump photon. So interestingly, in this setup, one more thing we have. So if we don't have any additional laser, definitely we'll generate a pair of photons and they are entangled. On the other hand, if you start with one weak laser, which is in this transition, in one of the transition of output photons, if you start some weak input laser, the generation of twin photon pair gets really stimulated. Stimulated means it really generates you bright beams. You generate trillions of photons here and trillions of photons here, and they are pairwise correlated. And in turn, they give you a beam, really bright beams, which can give you quantum correlation properties. So this kind of beams we call bright squeeze light. So squeeze light, if you don't have any input beam, it will give me squeeze light, but I want to make it really bright. Bright means you can see with your naked eyes. Then you seed the process and then stimulate this process and generate it. So now, having said that, definitely you can generate these bright beams. Now, how do I know that, or what do I need to do to check that whether they are quantum correlated or not? Or what is checked to show that they are quantum correlated? So for that, we can remember our first slide when I have introduced to you the short noise limit as well as squeezing. For short noise limit, we look at the noise of a laser beam. What we do, we get a laser beam. We split a laser beam into 2 parts. We just basically make 2 modes out of it. And then if we generate simple intensity difference measurement, and then we get some noise. Noise means intensity fluctuation at different frequencies. And then for the laser, I get this intensity fluctuation, which is normalized to 0. So it is called standard quantum limit. This is the minimum noise I can get with this any of the classical system. Now, then later what I do, I repeat my measurement with the bright twin beams that I have generated. I use, instead of laser beam, I have already generated 2 bright modes. I put 2 detectors here, 2 photo detectors here, and look at their difference signal. And if the difference noise is more or less, and then in this kind of system that I have shown earlier, we have shown that their noise is way reduced than the noise of the short noise limit or noise of the standard laser. So that means this noise reduction from the short noise limit, this is a squeezing. And then usual measurement of squeezing is done in dB scale. In this system earlier, we have shown about 9 dB reduction. That is 87% noise reduction from your standard quantum limit. So this is the simple and very easy measurement to check whether these beams are squeezed or not. Of course, we have the setup. This is real setup we have at IIST Trivandrum, where we have generated these kind of bright twin beams. We call them probe and conjugate. This is the entangled twin beam images from our setup, and then this is real setup as I told you. And then as of now, we could observe about 7 dB of the intensity, because with this setup people have generated about 9 to 10 dB. So we have already observed about 7 or slightly over 7 dB squeezing with the setup, which correspond about 80% noise reduction from the short noise limit. So once we have generated this squeezing, okay, one thing I must tell you here, that once I am looking at the intensity difference squeezing, then I am looking only one quadrature. Remember, in the very early slide, I have shown you can look at sine and cosine component. You are not here. I'm looking only one component. To look at the sine and cosine component, you have to go a step forward, and for that, the method people use or we use is called homodyne setup, in which you can look at the phase dependent noise of your beams. For looking the phase dependent noise of the beam, definitely we have set up a homodyne detection in our system. So what we have done, we are measuring, we are generating twin beams. And for homodyne detection, of course, if you are not expert, no worry. So we have to mix with the mode that I want to measure, we have to mix with a strong local oscillator. And then we look at the joint measurement of these two beams. And then with the joint measurement, we have satisfied the inseparability criteria. And then that shows that the beams that we have generated, they are quadrature entangled. So this is the, another check of the quantumness, or I would say, one more powerful check. Squeezing is only one quadrature, entangled, you are looking at both quadrature, and you are showing those beams are entangled. So now, having said that, something I'll tell you here, in the spatial domain, what we have done, or these kind of systems are capable of doing, so they are capable of showing the Einstein-Podolsky-Rosen paradox in their original form, or even with the bright beams, the beam which are macroscopically visible, you can see those beams, and even with those beams, you can show EPR paradox. So what, just for the beginners or the people who are not familiar about this, what is the EPR paradox? So in 1935, Einstein with his two colleagues wrote one of the most influential or controversial paper of the last century. Actually, if you look at the title of this paper title says, "Can quantum mechanical description of physical reality be considered complete?" They were questioning the completeness of quantum mechanics. So what they have demonstrated, they have visualized a thought experiment in which they have considered a pair of particles, two particles which are perfectly correlated in their position. And if I want to write the same in the quantum mechanical description, I can write the state of the two particles which are perfectly correlated in position like this. So if I make a measurement on a particle A, let's say I get X prime, then definitely I'm going to go or get the position of other particle as X prime. That's what it means. Now, if you have this kind of system, and then if you write the same system in the momentum description, of course, this is a little bit transformation, basis transformation, or basis change of the quantum mechanics. If you want to write the same system in the position basis, it happens to be like this. So that means it tells you that if two particles are perfectly correlated in their position, they will be perfectly anti-correlated in their momentum. So that means if you know the momentum of one, definitely you will be going to know the momentum of other particle. Now, so far so good. Where is the paradox? So paradox is something like that. So if, let's say, two particles A and B are in your lab, no problem. If A and B, two particles A and B, if you make them very far apart, like space-like separated. Space-like separated means you need to have, to have instantaneous influence, you need to have a communication faster than the speed of light. If they very far away from each other. Then what happens if you, let's say a particle is in your lab, and if you make a measurement on particle A, then definitely if you want to make a measurement on position of particle A, if you get a measurement of the position of particle A, definitely you're going to know what is the position of particle B. Same thing, if you are making a measurement on momentum of particle A, definitely you're going to know what is the momentum of the particle which is far space like separated from you. Then it turns out that the particle B is carrying, because if you consider like these two are two separate entities, it turns out that particle B is already carrying, because by measuring A, you can infer the position, and by measuring A momentum, you can infer momentum of B particle. That means that it appears that the particle B is carrying definite position and momentum values, which is against the spirit of Heisenberg uncertainty relation. And definitely this is EPR paradox, which was later solved because this EPR paradox arises because considering the local realism of quantum mechanics. But now we know that quantum mechanics is non-local, things can influence, even they are space-like separated, and then that mystery was resolved by just talking about entanglement and all, when we consider the quantum mechanics non-local. So this is all about it. And then this kind of experiment, this kind of scenario, they were Gedanken experiment, and they have given some thought experiment. But for the experimentalist, the Margaret Reid and Grumman gave a criteria that if an experimentalist makes a measurement on particle A, and then infers the uncertainty of particle B, and if the inferred uncertainty product is less than h bar by 4, then this is the way to show that they are in the spirit of EPR paradox. So that is the idea in this paper they have given for the experimentalists. And then in the experimental domain, in actual position and momentum degree of freedom, the first experiment was performed by Robert Boyd group in 2004, where they have created a pair of photon by a process called spontaneous parametric unconversion, where they have created a pair of photon, and they make a measurement on a particle A, position and momentum, and they look at their inferred uncertainty product, and definitely it was less than h bar squared by 4. And in that way, they have demonstrated EPR paradox in real position and momentum degree of freedom. But it was not until 2021 when we came up with, can we show the EPR paradox kind of situation in the macroscopic twin beams? If you have a bright beams, you generate these really bright beams, and can you show the EPR paradox with this entangled macroscopic twin beams that I have shown to you the way we have generated? And then in this particular work, we have, of course, looked at the position correlation as well as momentum correlation of the photons, or the photons in those beams, and then we looked at the inferred uncertainty, and then we have seen that inferred uncertainty product is definitely less than h bar by 4, and that gives again another way to check EPR paradox in the bright regime. So I'll not go to detail of what we have done, but if you are willing to know, then I can answer that in the question and answer session. But the point that I want to mention is you can generate bright beams. You can look at their position degree of freedom. When I'm looking at the position degree of freedom, I'm looking at the position correlation. Position correlation means where these photons are born, because these photons are born at the same place. That means their birthplace is correlated. So I will I will image that birthplace to my detector plane and then look at the correlation of those two. And on the other hand, to check the momentum, I will go to the Fourier transform domain and I look at the momentum correlation. That's how we have done the momentum and position correlation. And then one of the very interesting aspects of these kind of experiments was, so in the earlier work, in 2004 work, to see the EPR kind of paradox, people have to generate, or people have to get, let's say, billions, or not, if not billions, millions of images, or millions of single shot exposure to your camera or detector. So it was time consuming, but in our experiment, since they are already bright, you can show these paradox with even less than 10 images. You just get those images. Even single image have that capability to show the EPR paradox. That is the promise of the bright beams. If you have bright beams in the single shot, you can show this kind of landmark experiments. So now, having demonstrated this, EPR paradox, then we came up with an idea that can we use these kind of entangled bright twin beam for some cryptography application, or in particular, can we securely encode some information on those twin beams or not? For that, the same setup whatever I have shown, that I told you that in that setup what we are doing, we are absorbing 2 photons and emitting 2 photons, and then we are stimulating this process by starting some laser which is in this transition, and in turn it gives you bright beams. Ultimately, the main role is played by a POM beam, which is absorbed and then emitted. This is a 4 photon process which is happening like simultaneously, I would say, within the time scale of the process. So now what we have done, we have, instead of typical Gaussian laser beam, we have added some modulation to this POM beam. We have phase modulated this beam. Let's say I want to encode this pattern. If I want to encode this pattern, that based on this pattern, I have modulated the phase of my POM beam. And since this POM beam is absorbed by the atomic media, and then this information is transferred to these 2 beams, then how I can decode the information that is already encoded to the POM. That was the whole idea. So if we look at the individual beam, or the autocorrelation of the individual beam, we could not see any signature of the pattern that is encrypted. If I look at individual beam image or autocorrelation measurement, I could not see any information of the pattern to be encrypted. But on the other hand, if we look at the cross correlation of this, the cross correlation measurement of this with this, then we could clearly see the pattern that was encrypted in our twin beams. So in that way, one can securely encrypt the information in the spatial correlation. One thing is we are modulating these beams spatially, because this is a spatial pattern in a single shot we are encrypting. And then ultimately we are decrypting those beams by looking cross correlation. And these are some simulation results we have. So having demonstrated that in the spatial domain, the spatial correlation we are using, and then decoding that. And very recently we come up with another technique. Instead of spatial correlation, as I told you, that we are creating a pair of photon. Twin photons we are creating. But I said that these photons are created in random, but once one is created, other pattern also has to be created. Then can we generate standard quantum random numbers by using those twin photons that can have cryptography application or quantum key distribution application? For that, what we have done recently, so this is the work. In this one, the setup is the same. We detect these 2 beams, by 2 photodetector, and individually photodetector, they are looking at the temporal noise of this detector. And we analyze the temporal noise of this detector. And then if you look at the temporal, this is a real experimental data. The way the photon comes in here, they are perfectly correlated. This is a real experimental data that is showing this detector is giving you intensity or current output. If you look at the current fluctuation from here and here, they are almost perfectly correlated. And now what we have done now, and other thing I must tell you here, that if you look at individual beam noise,
these individual beam noise are much larger than the short noise limit that I told you, that individual beam are in thermal state. They are much larger or much noisier than the short coherent state. You can see that they're very noisy. These two beams are very noisy. Their noise level is much higher. But if you do a difference detection, their noise gets reduced. Actually, here in this particular experiment, it was 6 dB of the squeezing we have observed. And then with this, we have generated a random sequence of random numbers here and here that could be useful for cryptography application. Now, this is toward the cryptography application, and I will tell you some more thing about, what more thing you can do with the bright beams. Some of the work that we have been doing is spatially structuring those bright twin modes. So typically these modes are of the Gaussian profile. They have an intensity profile that is a Gaussian distribution, but we can engineer or we can control their intensity profile by our wish. Actually, we have generated these twin beam having this kind of parallel profile and then did some of the work. So in particular, we mainly focus on the orbital angular momentum imparting on those twin beams. We have, the orbital angular momentum degree of freedom gives you another tool to play with your light. The orbital angular momentum have a lot of application for high dimensional information encoding and quantum sensing. So you can encode or you can impart orbital angular momentum to those beams, and then you do the technology or whatever application aspects you want to do. And then moreover, we have looked at if we impart the orbital angular momentum to those beams, how their correlation from near field to far field they evolve. Some interesting result we have obtained, but it's not the right forum to talk about that here. So one very interesting thing which is under review still. So we want to talk to you is, see, we typically these beams, these are the Gaussian profile. Can you generate these kind of beams having structured profile, and then can you do with it? Can you play with some of the patterns, or can you look at the individual pattern correlation and all? That is the recent work we have done. In this one, what we have done, we have, instead of a normal Gaussian, pump was a Gaussian beam, Gaussian laser beam, but probe was a pattern beam. Probe beam, with this kind of pattern we can generate. We know the way how to generate this kind of patterns. We have generated, this is nothing but a superposition of two Legare Gaussian beams with the opposite topological charge. We have generated these patterns, and then that pattern induces another pattern to another twin beams, and then we get twin patterns here. And then what in particular this work we have done, this pattern, if you look at the measurement of this twin pattern at the near field, how these twin patterns are being generated here, and if they propagate, how do they behave? This kind of studies we have done. So this was the twin pattern image at the center where they are born, and if they propagate, definitely they preserve their shape. Their solution of your paraxial wave equation, they preserve their shape, and they are still twin patterns. Now what we have done, we have looked at the correlation of the whole twin patterns. The correlation we are checking by measuring the intensity difference squeezing. So we detect the whole beam, we send whole beam to the detector, other beam also whole beam to the detector, and then we looked at the intensity difference noise. And then with the whole twin pattern, we could see the noise less than the short noise limit. That means these beams are having quantum correlation. Then the next question we have asked, can you show some quantum correlation property in individual twins? So for that, what we have done, we have selected individual twins. We have selected individual twins, and then we have shown that individual twins also showing squeezing properties. So they are also quantum correlated. So in a way, if there are 6 patterns, each patterns are correlated pairwise correlated with its partner. So in that way, you can get a multiple channel in a single shot, or multiple bipartition in a single shot that can have application in the parallel information processing or parallel quantum sensing. So that was one aspect. Other aspect, we looked at it as follows. So we see these Patel's beams were already known in the classical optics. They self-heal, they revive their shape. That means if you cut one petal on propagation, it revives its shape. It heals by itself, just on propagation. And then this, of course, we cut each petal of each of the twin beams, and then look at the far field, they revived. And then we wanted to know that whether it's just a revival of intensity distribution or whether their squeezing also revived. So for that, these are the regions. Interestingly, once the whole petal was revived, the squeezing trace was almost similar. So the whole squeezing is revived. You can get the whole squeezing plot. On the other hand, if you look at individual petal, like pair 1, pair 2, pair 3, all petals still showing the correlation. That was something very interesting. You cut it, you got a new distribution, you look at the quantum correlation, and these distribution still preserves your quantum correlation distribution. That is really interesting. And other than we came to the point that, okay, instead of one, how about if you cut two petals, whether it revives? Definitely it revives. The shape revives, as well as the quantum squeezing properties also revives. That's what we have done. And another thing, if you cut one petal in one beam, and what happens to quantum correlation? So if you cut one, this is another very interesting aspect. So if we are cutting a pair, definitely we are removing, we are cutting the correlated partner. Then this correlation from the neighboring petals is getting distributed. But if we are cutting only one petal of the pair, then this extra petal in the another beam is acting as an extra loss or extra noise. And then definitely up to certain extent, squeezing is revived, but it is not as good as it was, because this extra petal, which was having some lone pair, it doesn't have its pair because pair has been cut, then it is acting as a additional noise to our system. So that is leading some noise reduction. So this is some of the work we are doing toward structuring this spatial quantum correlation and then application toward quantum cryptography. Just in next 5 to 10 minutes, because I started around 1:20-25. I don't want to delay you much, but just 10 minutes I'll finish. So some work we are doing for last 7-8 years toward the quantum sensing side also, just to show that these beams are having potential for quantum sensing application. I want to show some of the results. So we started this kind of work when I was in US, where we have interfaced this kind of system with some sensor we call plasmonic sensors. So what we have, or why? Okay, I'll give you a brief background. Plasmonic sensors are widely used in chemical and biological sensor, and they are commercial sensor as well. And then the point is, they have already shown to operate at their short noise limit. Short noise limit is the limit, the best limit you can get with the classical resources. Now, to go beyond that, you have to go quantum. That was our motivation. So for that, okay, I'll not tell you about these kind of sensors, but you just assume that these are some sensor, or they were like a metallic film in which we have a triangular nano hole, and then if you shine a laser beam or a light to those metallic layer which are having triangular hole, then it just makes the free electron of that metal collectively oscillates in the same, just a collective excitation of electrons, or the collective oscillation of those electrons, that is called plasmons. And that leads certain kind of resonances through those structure. And that, typically these are, if they are not plasmonic resonances, they are subwavelength structure, so light cannot penetrate through them. But if you are having plasmonic excitation, you can have light penetration through those holes, and you can get a certain resonances. And then if you are probing those sensors with a given laser frequency, you will get a certain transmission. You send a laser beam, you get certain transmission. Now, the point is, or the interesting thing happens in those sensors is, if something, some surrounding pressure change, temperature change, if you put some chemical, something, then whole resonance curves gets shifted. Earlier resonance curve was here, you put something here, then everything gets shifted. Then for your given laser beam, the transmission, the transmission of your laser beam gets changed. Then just by monitoring how much the transmission has been changed, then you can infer some substance around this sensor. That is the whole idea about plasmonic sensor. Now the problem is, if the change is much smaller, if the change of the transmission is smaller than the noise of light itself, you will not able to detect those smaller changes. On the other hand, if your light, the light is having really less noise, like squeeze rate, definitely you can detect a smaller and smaller changes. That was the whole idea. So for that, what we have done, we have, the resources are the same what I have been discussing to you. You generate bright beams. You probe one of the bright beams to the sensor. You send one of the bright beam to the sensor kept in this chamber. Other you directly send to your detector. Okay. So now you just make some changes of the refractive index around those sensors, and then look at how small changes of the refractive index of air around sensor you can detect. So for that, what we have, first we have, we have calibrated our setup with the coherent state or usual laser beam, and then we have seen that if we make a very small change, like of the refractive index, let's say 1.6 part in 10 power minus 7, if you make this much small change of the refractive index, you get a signal with the coherent state. Definitely, if you repeat the same experiment with the twin beams, then as I told you, your noise level is reduced and the signal height remains same. Definitely, you're going to get the quantum enhanced sensitivity in those setups. So that is the already improvement in the signal to noise ratio. But real problem happens when your signal is height of signal is same as the noise. Then you don't know where is this is signal, where is your signal? Then in that case, you don't know or you are not sure about the signal. At the same time, this is really a small change of the refractive index. If you detect with this quantum twin beams, you can even detect those signal which was buried under the noise with an enhanced signal to noise ratio. That's how you detect or you enhance the sensitivity of those kind of sensors with the quantum resources. So of course we have been continuing this work, and then over the time what we have utilized this was just a one sensor probed by the beam, one sensor probed by one beam. Now in my just earlier presentation, I have shown that, the few slides back, I have shown that these beams can have multiple spatially correlated region. So what we have done, as I have shown that this can be correlated to this can be correlated, different part of the beams are correlated. Now, in this particular work, we have interfaced these beams with a parallel sensor. We don't have not only have one sensor, we have a set of 4 sensors, and then look at the pairwise correlation at the different parts. And then in that way, we can, a single beam is sensing 4 sensors together. In that way, we could still improve the sensitivity beyond the short noise. You see what you see here in all black traces are the signal that was buried under the noise could be detected by this kind of quantum resources. And not only a single sensor, but a quadrant of sensor, 4 sensors sensing the change of the refractive index. So yes, this is toward the quantum enhanced sensing of the change of the refractive index or quantum enhanced plasmonic sensing. Now, very recently, we are working toward quantum enhancement on the other kind of sensors, optical sensor, in particular optical gyroscopes. The optical gyroscope or gyroscopes are ubiquitous. They are everywhere. Maybe it's a missile, rocket, spacecraft. Everywhere gyroscopes are used, even in our mobile phones, where they are navigation sensors. They tell you orientation, direction, and many things. So we wanted to focus on network of gyroscope. And then this work was done in collaboration with Professor G.S. Agrawal at Texas A&M University. So where we the resources we have, this is a theory paper in which what we have proposed that you can generate, you can have the bright squeeze state of light that as we have in our current lab. So you can generate these bright two-mode squeeze state of light, and then you can send these modes to symmetrical beam splitter network. Basically, these symmetric beam splitter network divides these modes to M modes. And then here also these are M modes, and these M modes are entangled modes. And then out of these, each out of these modes, probe is one gyroscope. If these output of modes probe one gyroscope, then can you, or how is the sensitivity goes in the overall network of gyroscope by using the quantum resources. So this is, for the distributed net quantum sensing, where you can put multiple gyroscope and then look at better sensitivity, phase sensitivity in the angular rotation of your whatever spacecraft or satellite, whatever you want to do. So in that one, our initial calculation or our calculation showed that, with this, definitely with the configuration that we have proposed, with this one, this is the short noise limit, and even the lossy cases, even if you introduce the losses, about 50% losses in our system, then you can get the quantum advantages. Whatever you see below than this dashed line is showing you quantum advantage. Smaller is this number, better is your sensitivity. And then definitely as your losses are decreasing, then your sensitivity is increasing. So we have shown that this kind of resources, that bright two-mode squeeze state of light, can be useful resource for quantum gyroscopes. Moreover, we have done calculation on the quantum Kramer-Rao bound, and then we have shown that definitely these kind of resources can quantum Kramer-Rao bound is ultimate sensitivity bound that a quantum system can give in the estimation of parameter. So here, what we have shown that the resources or the system that we are performing, it is almost saturating our quantum Kramer-Rao bound. So in a way, then the detection scheme we have chosen, or the system we have, it is capable of showing you to the and reaching you to the most advanced sensing platforms. So with this, I would like to summarize what we discussed in last, I would say, 45 to 50 minutes. We talked about, the motivation behind why you should care about squeeze light, or in particular, bright squeeze light. They are really bright. They are twin photons, not only twin photons, they are twin beams. And then we have shown that these twin beams can show squeezing. Squeezing means noise reduction from the short noise limit. That this is the classical limit. This is beyond the classical limit. At the same time, they are entangled. They can show the entanglement. And then, of course, they can show the EPR paradox or EPR kind of entanglement as well. These beams can be useful for information encoding, as well as to generate random number sequence for quantum cryptography or quantum key distribution application. You can engineer those beams as your wish. You can engineer, and then you can look at the individual correlation, individual bipartite correlation in those two beams. And then at the same time, you can show some self-revival of spatial quantum correlation on propagation. Moreover, at the end, I said, you can detect with those beams, you can detect something is buried under the noise. A signal that is buried under the noise, you can detect, and then these resources have capability to reach ultimate limits of the quantum. So with this, yeah, definitely, I would like to acknowledge the people with whom I have been collaborating over the time. Of course, these are my current PhD students. Jarin just recently graduated, and then these are just master's students who are working in my group in several projects. And then Alberto Marino is a long-time collaborator, and then now he's in Oak Ridge National Lab. And then Rafael Puzer, we work on plasmonic sensing work together, and recently we have been collaborating with Professor G.S. Agrawal.
So with this, I would like to thank you all. And then if you have any question, you please, I'll be happy to answer.
Thank you, sir. Am I audible?
Yes, 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 you are audible.
Sir, is not a question. It is just to supplement our thought. As such, we have electronic, photonic, and plasmonic. Yeah, these are three.
Excuse me. I did
as such, we can say that we have some. We can realize qubit in electronic system, spin system, as well as in photonic system, as well as also third one is plasmonic. Is it correct?
Yeah. So, no, for different kind of sensing platform, here what we have done is the plasmonic resonances. So what these plasmonic resonances, we want to see these plasmonic sensors, they are probed by the light. They are probed by the light. We are not really measuring the plasmons. We are looking the response of the plasmon on the light. And then with that, we want to enhance the sensitivity.
It will supplement your photonic system. Yeah.
Yes, yes, definitely. Yes.
But plasmonic, you need also, you cannot realize qubit with taking plasmon as a quantum particle.
Yeah. It's not for qubit platform. It's for sensing platform we have done. Yes. You're right.
But communication can be, communication can be also enhanced.
The plasmonic was one tool. See, we have these resources. One of the sensors they are used. So plasmonic was not motivation for quantum cryptography or quantum computation. So plasmonic was just a standalone project in which plasmonic sensor, based on the plasmonic principle, people use the sensors, the biological sensor, and then can we enhance the sensitivity of those? So it's not like we are using the quantum features of the plasmons.
Okay. Thank you.
Yes.
Sorry. Well, thank you.
Sure.
For it is just classroom teaching we are telling. Okay.
Yeah, sure. Thank
you. Can I?
And we need some because of for resonance we need some prism and prism coupling like that also. You need
yes. This we have done this extraordinary optical transmission, and then of course Kretschmann configuration is different configuration. Yes, they look on reflection geometry. We looked at in the transmission geometry. Yes.
So it is metal dielectric interface. Plasmon generally exists in metal dielectric. Thank you.
Yes, sure. Thank you.
So, can I ask a question? This is regarding when you do sensing, my mind goes into something else, that is what is called as quantum reading or quantum target detection, where entangled light has been used and it shows in the weak intensity limit, these behave very well. So I wondered if your twin beams would also be useful in such applications, that is target detection, or in the sense quantum reading, that is digital reading, where you do keep one as ancilla and other one as measured, so that you can retrieve what is the discrimination between zeros and ones that you do. So have you thought about it?
No, definitely. There be long time, with I work in, we have some initial collaboration, some discussion on the quantum radar kind of stuff. So where you probe, you use one of the beams to detect your target, sense your target, and look at the other beam you keep with you, and then look at the joint measurement. So that is the project we initially discussed, or I have already some idea. But the problem is in those kind of quantum target detection or radar, the losses are really huge. So in the losses system, if you look at the squeezing measurement, which are continuous measurement, these kind of this much losses they will not able to tolerate. So so far if you are looking at pairwise, photon pairwise, definitely
you just look at all, you just detect, you throw the other information, you only keep the information of your correlated photon pair, that is fine. But as long as we are doing continuous measurement, as we have been doing here, this won't be a right platform for this kind of lossy system.
Okay. Okay.
Yes.
But what I mean to say is, even if it is quantum reading, that is, say, for example, one develops some kind of DVD or something, and I want to read it. So in that case, it may be not a far away kind of detection.
No,
but the same principle works there.
Yeah, definitely. Yeah, very true. Very true. That's quantum reading, or in other language we say quantum imaging also. So so reading means, you know, so if you have a very poor signal there, whether with the quantum you can improve that. So we are working on, currently in my lab we are working on that project where we are illuminating one object by the one of the beams and then looking at the better resolution by doing joint measurement. Yeah, that, madam, that project we are working on currently. Sure. Thank you.
Thank you. One more thing is about your, sorry. So can I continue? Just one more question, that is on your experiment on the inferred uncertainty relations.
Yes.
So that is Marguerite Reed and others who had proposed. So that is something called steering.
Steering, yes.
So steering experiments also give you something like what would be a entropic uncertainty relation. Because one can do what is entropic uncertainty with the same kind of data. So that leads you to check what would be the kind of key rate for a quantum key rate, quantum key distribution. So I was wondering if it is possible for your.
It is possible. Recently, we have having some discussion with another Professor Archan Majumdar and SN Bose. Yes. So, some discussions are going on, but yeah, definitely we are looking at that aspects also, because it's a like similar thing what we have done actually. Yes.
All right.
It's possible.
Okay.
It's possible.
Yeah. Thank you. Thank you very much.
Just 1 minute. In case of radar, say for example, photonic radar, we have to tune radar cross section. Can you send plasmonic wave also in place of photonic?
No, plasmonic wave is having very short life. Actually, they are not propagating like through the phase space. Their propagation length is very, very small in the micrometer orders. Micrometer or just.
So I believe plasmonic cannot replace photonic.
No. For the photonic, see, if you want to have a communication, you need some flying qubit or photons which you can fly.
Okay. Thank you.
Yes. Yeah, sure.
Thank you.
Yeah,
I have
Professor
questions. Yeah, I have questions. In your presentation, first of all, thank you for a very interesting and informative talk. Allow me to ask 4 questions, but if it is not possible, then maybe we can continue in the lunch session if possible. So my first question is, in your presentation, you mentioned about 4-wave mixing process. So question, can we generate or create squeeze light instead of atomic media by using, for example, micro ring resonator?
Yeah, definitely. We can use, it's like, as long as you can, this micro ring resonator allows you to generate this kind of, synthesize this kind of Hamiltonian, definitely it will be useful. But the problem is the kind of interaction. I'm not very sure about what material you will use and all. It's the technicalities, I'm not sure. But micro ring resonator, like if you want to use 4-wave mixing in micro ring resonator, or people use in the fiber also, optical fibers also, they can make a 4-wave mixing and then create squeeze light. Similarly, with the micro resonator, I believe that it should be possible. You have to, it's a matter of proper material selection and then proper pumping system. Yes.
I mean, silicon nitride people are using, and you may get more squeezing. Second question, on slide 12, you have discussed joint measurement in two mode states. I mean, the quadratures x1 and x2. So, so when you're talking about x1 and x2, are they non-degenerate modes or degenerate?
They are non-degenerate. They are non-degenerate mode. X1, X2 are non-degenerate mode. That's why we had to our homodyne system was little tricky. So let me just, because I rushed it through, I thought, okay, this is just for expert audience. So here, because these two modes are non-degenerate, the red and then yellow was non-degenerate. So when I want to homodyne with the yellow, I have to have a local oscillator at that frequency, and then the same for the another mode. So for that, the local oscillator is created by another four-way mixing in the same system. So the local oscillator is also created by a four-way mixing in the hot atom in the same cell.
So my question is, how do you measure their quadratures? I mean, x1 minus x2 and p1 plus p2, since they are non-degenerate, and you will see beats. I mean, frequencies are different.
No, see, okay, the question is, once you are looking at the quadrature of, if you look at this beam, let's say this is x1, and then x1 quadrature you get from this balance detector. You get this one x1, and then you get this noise of x1.
Okay, you are adding after detection.
Exactly, and another also x1. You are adding or subtracting after that. Yes, through the hybrid junction. Yeah, electronically we are doing that.
My third question, what is the achieved squeeze level in your experiments with vapor media?
So very recently, around 7.5 dB we have achieved it. Yeah.
Thank you. My fourth question.
In my earlier group, we have achieved about 9 to 10 dB. We have some technicalities, but more than 7 we can observe in my current lab.
So my final question, in topological charge beam experiment, did you study robustness of these beams to diffraction and losses, I mean scattering and absorption, when they are propagating in the free space?
Yes, that's a good question. So in this paper, we have exactly done the same thing. So what we have done, these beams, I don't have result here, but these beams we have generated, like both the twin beams were not just, they were not Gaussian, they were not having a Gaussian profile, they were having LG profile. And then what we did in this LG let's say this is a LG, another is, let's say this is LG1, that will be LG minus 1, and then we cut it. We introduce the asymmetry or perturbation by clipping those, literally clipping those beams, and this beam also getting clipped. And then we looked at the propagation. On propagation, we look at the far field, or let's say 200 meter or so, not 200, sorry, 2 meter or so in the far field, whether their orbital angular momentum is preserved or not. So that's how we have done.
So does it mean that you are using again the same media, that is vapor media?
No, this is generated in the same media. These beams with the Laguerre-Gaussian profile or OAM, they have already been generated in the same media here, but their propagation was on free space. Space. And then we generated and we clipped them and then let them propagate it through the free space. And then whether they recover their shape or not, or their shape as well as their angular momentum or topological charge. Indeed, they do. That is the PRA 2024 paper.
So does it mean that you are using two pumps? One is Gaussian and another is Hermite Gaussian. Am I correct?
So no, in that one, what we have, we have used the same pump, but the probe we have used to generate these kind of beams, the pump was Gaussian, probe was a Laguerre-Gaussian. So probe was Laguerre-Gaussian. If you have a Laguerre-Gaussian probe of L equals to -1, then L equals to +1, then you generate conjugate -1. So this was Laguerre Gaussian only. This was just a Gaussian.
So you have four-way mixings, and then you should have, I think, if I understood correctly, two pumps. So both pumps are Gaussian. My question was.
Okay.
Or
you are right. You are right. That these two ultimately there are 4 photons needs to be involved. You said 2 degenerate pump. They are the same. One from one pump. 2 photons. Same 2 photons from the same pumps are taken into account.
Yeah.
So they are not physically 2 pump. They are physically only one laser beam, but the photons from that laser beam can drive this transition as well as this transition. That's how 2 photons from the same pumps are used.
Okay, it's clear. Thank you.
Yeah, sure.